Hi, I'm Casey Duckring. I'm a PhD student at the University of Chicago. I'll be presenting Virtualized Logical Qubits, a 2.5-dimensional architecture for error-corrected quantum computing. This is joint work with Jonathan Baker in collaboration with Professor David Schuster and my advisor, Professor Fred Chong. So currently, we are in the NISQ era of quantum computing with noisy, small devices that may become useful for some things, but the long-term goal for quantum computing is to reach fault tolerance, where we need millions of qubits to perform well-known algorithms like Shor's and Grover's algorithm. While this is still a bit far out, we need to be considering potential architectures for these systems now so we can start developing the technology that we need for those. So there's many challenges to scaling up these systems to millions of qubits. So for this talk, I'll be focusing on superconducting qubits in a dilution refrigerator, and there's some main issues with these things, scaling them up. Such as crosstalk error, which is error between qubits that are near each other. You have many control wires that you have to engineer and fit into this refrigerator. And you also have things like fabrication consistency of many, many qubits on a silicon device. So for this talk, we'll present an architecture that attempts to sidestep many of these issues or reduce their effect through architecture design. So there's many approaches to this that have been discussed in the past. It can be boiled down to two main ideas. So modular devices, where you have many small, easy to build devices connected by interconnects. Or there's the like a classical route where you take memory separate from compute and you have a bus to shuttle from between memory and compute. In this work, we look at qubit local memory technology, and that's actually well suited for this, and show the unique characteristics of quantum computing are well suited, particularly because quantum computing computes in place on qubits stored in physical devices. And we'll adapt a state-of-the-art 2D error correction code called the surface code into this sort of 2.5-dimensional architecture where the third dimension is the index in this memory. So now I'll go into a little bit of background on error correction and this technology before I get into how we do the actual architecture. All right, so for quantum error correction in superconducting devices, you have this grid of transmons here on the right, and these lines between them indicate actual connections between them that allow operations, 2-qubit operations on 2 of those qubits. And we use this grid because this layout is well suited for the surface code error correction, although there's many other codes. So to do error correction, you do these parity checks shown in these colored boxes. And so 9 of these data qubits shown here represent a single logical qubit. And so just as an aside, there's 2 types of parity checks, phase and bit flip parity checks. In classical computing, you'd only have to check for bit flip errors. But this is 2D because each dimension checks for one of those error types. Here's a picture of a representation of a single qubit state. The classical 0 and 1 states on the top and bottom, and a quantum state is anywhere on the surface of the sphere. So bit flip flips between the top and bottom by rotating around the x-axis, but a phase flip rotates around the z-axis, which wouldn't have an effect on a classical state, but does if there's quantum information stored. So the way you perform operations on these systems are by performing many unreliable operations on data qubits to do reliable operations on the logical qubit. and you perform error correction periodically to keep errors from accumulating over time. To do 2-qubit gates to actually perform computation, there's existing methods called like braiding or lattice surgery, and we use these also, but then show some additional operations that our architecture shows. So the technology that we take advantage of in this work is superconducting cavity technology, although any similar technology would also work. So this is where you have a cavity that can store photons with quantum information. So you can store, and we say about 10 qubits per cavity, and this transmon qubit at the top can randomly access any of the qubits inside to load, store, or do a 2-qubit operation. And the advantage of this is that you have a single set of control lines to this transmon to control all of the qubits in the cavity. And stored qubits last around 10 times longer in this cavity. So now I'll get into the actual architecture of this. So we take this 2D grid that I showed before, and we cut up all the different logical qubits and layer them into these memories spread across them like this. So this basically virtualizes these physical addresses in this working memory on top into the storage below. So this gives like a physical virtual address separation. And then we would use the transmons to load a certain logical qubit and apply error correction or compute. And we need to periodically load all of them to correct for any errors they had during storage, just like a DRAM refresh or something like that. So this architecture saves around 10x transmons, but it turns out that there's actually some other benefits that we get because of this layered layout instead of another layout that we might have chosen. So because we now have stacks of these logical qubits, we can now load one of them to the top, and then since they're parallel to each other, we can perform transversal operations like this logical CNOT, where we do a 2-qubit gate between these 2 qubits directly and without having to use lattice surgery or braiding, which involve turning on and off parity checks. So this is not possible in 2D because this connection between all the corresponding data qubits isn't possible. And it's 6 times faster because it takes 6 time steps to do this otherwise. With lattice surgery, it looks something like this, just as for comparison, where you have to turn on and off these parity checks. But don't worry about understanding this bit. Okay, so finally, we'll get to evaluation. So we're comparing our architecture, a couple variants of it that we look at in the paper, versus this baseline with 10 times more qubits. So for errors, we assume depolarizing error, which is a good approximation of real errors. It's actually a worst case, but we do not assume that there's correlated errors. We assume all errors are independent. And we perform 2 million simulated trials per data point in order to compute the low logical errors that we achieve. And for more details about this, you can check out our GitHub repository with more documentation. So these are our threshold evaluation plots. So the key takeaway of this is that they show that our architecture does work for error correction just like the baseline. But to read this, basically the x-axis is the physical error rate of the device, and we combine all the different parameters the device has and into a single error parameter so that we can find a single threshold to plot. And then the y-axis here is the logical error rate you achieve with different distances of code. The code I showed before was distance 3. If you increase it the size of it, you can distance 5, and so on. So the threshold here is when increasing the code distance actually decreases the logical error, meaning that the code distance helps instead of hurts, because you're performing more operations to do the error correction, but there's more redundancy, so you actually get benefit. And the thresholds are all essentially the same here. So that's good. That means that the overhead of loading and storing from memory and being left in memory for a long period of time is not very detrimental to the code performance. The other thing to look at here is the slope of these curves. So a steeper slope means that the code is better as you decrease your physical error rate, you get a faster decrease in the logical error rate. So for our main variant, or basic variant, it gets almost the same slope as our baseline. The others get slightly shallower slopes because of the overhead of extra gates to load and store, but not actually much lower. So you only need to have hardware that's slightly better than the baseline hardware. But this is actually easier to do because you now have 10 times fewer transmons to tune and worry about crosstalk with. So in conclusion, realizable quantum error correction protocols are a critical step in the path towards fault-tolerant quantum computation. So we set out to exploit this memory in a 2.5D architecture, and we showed that we get a compact scalable architecture and also get some nice extra benefits in terms of speed and data locality from that. Some downsides to point out are that this memory technology is relatively new. It's been proven by David Schuster, but there's still a lot of work to do to improve it to levels of current superconducting devices are. But it's just a few years behind those. And you serialize operations by a factor of 10, but this is just an artifact of using memory. But because we use memory, we get a 10x increase in lifetime, so the only effect is that your program takes 10 times longer to run. But for quantum computers, the biggest metric is the ratio of how many operations you can do total before you error overtakes your values. So the benefits we get, though, are we get this huge reduction in hardware complexity. We have 10 times fewer transmons and control hardware and control wires and all that. And we get faster execution via the transversal CNOT I showed. And it turns out that this gives us a 1.22 times speed up in magic state distillation. For error-corrected algorithms, this is the major cost of any algorithm execution, is generating t-states. So this is a big win. Final thing is that just higher data locality means that there's less communication congestion, and this third dimension and the transversal CNOT gives us the ability to do more operations with less communication. And so we hope this work motivates further experimental efforts and prompts industry to adopt and scale up this architecture. And the smallest proof of concept of this that can give you 10 logical qubits requires only 11 transmons with 9 cavities. Thanks for watching.